So who we got on here then? Let's have a look. Oh, there's all sorts of people. Great. Right. Let me share my screen.
Hello, Chris.
Hey. Good to see you all.
Yeah, the same. Tony has the biggest monitor that I have ever seen. If anyone,
yeah, I've just switched it onto a smaller one because it's impossible to do on there. Right, let's have a look. Right. Yeah, you'll have to forgive my my lack of familiarity with screen sharing on Zoom. Where are we?
No problem. So you're in the Mac OS application now, right?
Yeah, yes, I am.
So if you just move your mouse, you will see it at the bottom of the screen where you have participants, chat.
Yeah, I've got that, and I've got the window come up, and I'm just trying to find the app I want to share on my in the list of things that should be shareable. Let's have a look.
If it's already full.
Oh yeah, got it. Here we go. Right, okay. That's it. Right.
Great.
Okay, perfect.
Great, welcome Tony, and welcome everyone back to the TRIPS meetings. And we're very happy that Tony will present from the Stockholm team. I think we have decided on the schedule that we will meet this time the first Tuesday every month. So in April, Pei Wang's team will speak, and in May, Chris Torreson's team will speak, and in June, Antonio Kella's team. So please go ahead, Tony.
Okay, so it's great to be back in the TRIPS meetings. My talk today is going to be on forthcoming book, which is called the Unified Principle of Cognition, and the system that is developed on the basis of that, called Insight. So very quickly, for those who don't know me, who am I? I'm a guest researcher at Psychology Department of Stockholm University. I work with Robert Johansson and Patrick Hammer. I've been working on AGI for over 25 years. In the early days, I worked with Ben Goetzel and his team on Novamente, which later became OpenCog. And then I transitioned to what I call a pure NARS, as NARS philosophy was a big part of the initial thinking around Ben's implementations. But I preferred Pei's approach, so I ended up going with the NARS, the pure version of NARS, so we call it. And I've been working on what I call NARS philosophy-style AGI systems ever since. OpenNARS, Narja, Alan, Owner, all of these systems over the years. So the agenda for today, very quick overview of what I call the historical foundation in the NARS philosophy, just in case there are people who don't have an overview of that in their heads. What do I mean when I talk about a unified principle of cognition? And then we'll get into the meat of the talk, representation, which is essentially spiking neural networks, the logic, the motivation system, the control system. Then we're going to look at how psychological processes emerge as a result of these higher level concepts. And then we'll look at the software architecture. Now, I should stress, this is what I would call a 10,000 foot view of this system. It's a big book. There's an awful lot of information in here. It's impossible to go into detail on every aspect of this. So this is really a taster to give you a flavor of what's possible. And if you're interested enough, you can read the book. All the details are in there. Or you can talk to me. I'm happy to discuss it at length. So without further ado, let's dig in. So very quickly, what do we mean by NARS philosophy? architecture. Well, essentially, the key points here are the assumption of insufficient knowledge and resources. And I'm not going to go into this in huge detail. It's more of a reminder because I think most people will be familiar with it. Hello?
Oh, sorry.
Okay, no problem. Yeah, just as a brief aside, just in case, if we could keep the questions to the end, because there's a lot to get through, just in case people start asking questions. Hang on till the end, and we'll do what we can with the time available. So ARKR, with the assumption of insufficient knowledge and resources, grounding principle of Pei's NAS philosophy. Three key components have been finite system, a real-time system, and open to information in any domain, any time. Experience grounded semantics, which means it learns from its interaction with its environment. It isn't pre-trained. Everything it learns, it has to experience. And some key aspects of NAS are a non-axiomatic logic, which is a syllogistic logic inspired by Aristotle, an adaptive learning and self-organizing system, concept-centric memory structure, and temporal and contextual reasoning. And I think I'll leave it there. There's an awful lot we can talk about in NAS, but those are the key components. So when we talk about a unified principle of cognition, what do we mean? Well, I've tried to give it a definition, although there's probably a million and one ways of looking at this. The definition I'm using is it's constructing a continuously adapting, dynamically self-organizing behavior map grounded in environmental regularities given insufficient knowledge and resources. So that's a bit of a mouthful. So what do we mean by this? Well, constructing, it's a constructivist approach. It builds from its behaviors and experience with reality. So it develops a network of understanding of its environment, both internal and external. It's important that it's both. It doesn't just learn about the outside world, it learns about its inside world as well. Dynamically self-organizing. So essentially what we mean by this is that we don't need to do anything to it for it to function. It structures its information on its own recognizance, including new knowledge and modifying its own operating processes, not necessarily changing things at the meta level, but organizing its information as it experiences it. The behavior map, which is really the core of this system, it's a network representation that captures the experience of the system. And I would talk about this in kind of three dimensions. It captures elements in time, in space, and in behavior. And those three things integrate together to form maps, which we'll look at in a bit more detail later on. Continuous adaptation. It's a system that learns in an ongoing basis. It's not like a deep learning transform model where it's trained and is static. It continuously adapts based on its input and its own experiences that can also be internal. And finally, recognizing regularities. Essentially, pattern recognition is what we're talking about here, both internally and externally. The idea is that the system is grounded in the regularities that it encounters. So that's a key component there. The small graphic that we talk about that's on the right-hand side, some aspects which we'll talk about in a little more detail, but essentially emergent behaviors and holistic integration, they're key components that the model supports. We don't program in every aspect here. The idea is that emergent behavior is what we want to see. So it learns from its environment and behaviors emerge both at a system functional level and at a behavioral level. And the holistic integration is essentially, you get more out than you put in. The sum of the parts is greater than the pieces. So let's move on. So to the representation. Essentially, it's a spiking neural network, but with some differences. I'll briefly go over this because I imagine everyone knows what a spiking neural network is, but just for those that may not, we'll cover it quickly. Unlike a traditional ANN or recurrent neural networks, etc., spiking neural networks, they work on slightly different principles. They have spikes, which are essentially energy or action potential injections that shoot across links between nodes. They typically don't have any semantics. They are literally node spike models. The key thing here is that the timing of spikes is the crucial component of spiking neural networks. So when a neuron fires, it activates a spike, and the spike can travel along different synapses to different spikes. It may or may not, to different neurons, which may or may not activate depending on what their action potential is. Now, this interaction between spikes and neurons essentially encodes reality in the system, represents what behavior the system is undergoing. And there are some key benefits to spiking neural networks. I mean, first of all, they're biologically plausible. The brain is based on them, obviously. So that's a useful way of thinking about problems, is that we have a working example of them, and we can learn quite a lot from how the neuroscience works. They're particularly effective for dealing with temporal dynamics. So where you have fast-changing dynamic scenes that you want to capture, spiking neural networks are very effective for that particular usage case. They're also very energy efficient, unlike large data centers where we have these deep learning models where you need a nuclear reactor for each data center. They can essentially be very, very energy efficient. They can be weakly connected and sparse connections, and they can be localized as well in terms of local updates. So useful as a way of thinking about an alternative to these high energy deep learning networks. I'll push on. We'll keep going through this as quickly as we can. So I've mentioned a couple of these points. One of the key aspects on here is this last point about synchrony and polychronicity. The key thing about spiking neural networks is that the timing is very, very important. And interestingly, they can represent more patterns than the neurons, than the current number of neurons that exist within the network, based on the way the timing works. And I'm going to give you some examples of that in a moment. Just to quickly understand what we mean by neurons, this is in fact the model of the neuron that we use in Insight. It's not exactly the same as a biological neuron, but there's a lot of the same components. So we have the idea of a spike, action potentials, thresholds, and refractory periods. And what do these mean? Well, essentially, when spikes arrive at the neuron, they accumulate an action potential, and it can decay over time. So it may drop before it actually causes the neuron to fire. But if a neuron actually reaches a threshold, which can be dynamic, that neuron will fire off another spike. Once that neuron has fired, there's what's called a refractory period. So it means it cannot fire again until that period has expired. And there are two refractory periods here. The absolute refractory period, which essentially means whatever happens, it will not fire within that period. And then there's the relative refractory period, which means that it has to have a much higher action potential than it would normally have if it's going to fire. And that will gradually decline to the point where it returns back to normal. So there is a period where it can't fire at all. Then there's a period where it can fire if there's something extremely high, which allows it to respond to something particularly important. So that's essentially the model for the neuron. And just to give you an idea of how these things work from a timing perspective, top left A, we've got 5 neurons and some interconnecting synapses with the appropriate propagation delays between, let's say, B and A 1 millisecond, C and A 5 milliseconds. And this is the amount of time it takes a signal to travel between those things, or alternatively, you can think of it as if B occurs, then 1 millisecond later A occurs. It's kind of like a predictive link. So if you look at B, you can see that there are different, if these all occurred at the same time, so B, C, and D, then there would be different synapses firing at different times. When you look at C, what you can see here is that if D and C and B all fired at appropriate times, then you could fire A, because they would have enough signal strength, assuming that you need these 3 activations to trigger A. That would trigger A at a specific time. So the timing sequence is critical to enabling A to occur, and it essentially means that the sequence of D, C, B with the relevant propagation delays is represented in A. So that's essentially a sequence that A would cause to be fired. And then again, D, even though it's using the same neurons, with different timing, it can fire different targets. So the idea here is that by changing the timing of the spikes, the patterns that are fired can be quite unique, and there can be a lot more patterns that are represented in the temporal patterns than actually are represented than the neurons themselves. So there's a couple of orders of magnitude more possible temporal patterns than the neurons actually represent. So that's just to give you a flavor. I'm not expecting anyone to take an exam on this. In fact, we'll skip that one. Right, so Hebbian learning, I'm sure everyone is familiar with Hebbian learning to a degree. Essentially, it's the idea that neurons that fire together wire together. It's great for associative learning. It's not enough on its own, and there are some issues with it, but it's a good tool. And I'm going to refer to this as what I'm calling associative learning. And the key issues here are it's difficult to represent nonlinear relationships with Hebbian learning. It doesn't do temporal dynamics very well. Some, but not great. And high-level abstraction can be problematic. So why am I using Hebbian learning? Well, there are some really good strengths. It's biologically plausible. It does efficient unsupervised learning. It allows local updates where you only need to adjust the weights that are connected, not the whole model, unlike probabilistic style models. It's very good for feature detection, but there are issues. So overfitting correlations, lack of error correction, stability issues, and limited complexity. So these are challenges. But what I can show you is that by adding in predictive implications, which are a form of temporal timing, we can overcome all of these issues around associative links and Hebbian learning. So is spiking neural network, is it sufficient for an AGI representation? Well, this is the question I asked myself at the start of my project. If the neocortex really only uses neurons and synapses, is this sufficient? Why can't it be enough? So what is the minimum model that can be used to capture the complexity required? So I began with the idea of time. Oh, where are we going? Time being the fundamental grounding principle of both insight and spiking neural networks. This is a bit different to Pei's model, where Pei begins with inheritance. But I've always wanted to start this model beginning with time. So I've started the idea of the grounding principle here is time. And then by introducing Hebbian learning and temporal linking, I believe all forms of relations can be captured in a spiky neural network. So in order to do this, we need some form of logic. Where do we create information? How do we infer and do inference? Well, the key is what I'm calling HONAL, higher order non-axiomatic logic. And I'm more than happy to say that this has evolved from Pei's non-axiomatic logic. A lot of commonalities, syllogistic logic, evidence-based, truth functions, experience-grounded semantics. The difference is here is that it's what I'm calling it's a unified neurosymbolic framework. It's not an inheritance logic, it's a different kind of logic, but it does inherit many of the properties of now. The two sides of this are, there is a neuro-style representation and there's a symbolic style representation. And we'll go into some of that now. So the grammar, let's just talk about this. What do we mean by grammar here? Well, there's a very minimal semantics. There are two types of links, predictive and associative. And there are two types of nodes, percept nodes and binds. And we'll see what those are in a moment. But essentially, predictive links are temporal predictions, which have an associated propagation delay, essentially a synapse. And we have associative links, which are essentially Hebbian links with no temporal component explicitly represented. There are no explicit symmetric relations. So this is essentially the full set of links and nodes. We have a spike, which is an action potential, and we have a percept node. Now, a percept node, all percepts enter in the system as a symbolic percept node. And they can be something as simple as a pixel or something as high level as a sentence. Percept nodes are system specific, and you can have them based on your perception system. So for example, if you use YOLO, you can have a percept node, which is a YOLO representation of the word and bounding box for that particular perceptual input. Or as I mentioned previously, you can have percept nodes, which are literally for a pixel. And you can have them both at the same time if you want. And you can, in fact, associate a pixel pattern with a YOLO high-level symbol, which turns out to be quite useful. Binds themselves, they're essentially ways of grouping components together. Temporal binds are temporal associations, and we saw at the beginning where in a spiky neural network, multiple synapses leading to the activation of a specific neuron with temporal sequences that match it. There could be 2 or 3 inputs. That's essentially what a temporal bind does. It allows multiple inputs to go to a node to trigger temporal binds. The same with associative binds, except there's no timing associated with that. They are just essentially they're compositions of nodes. And you'll note that the difference here simply is commas are temporal binds, semicolons are associative binds. In terms of the grammar, we have predictive links, which are the fat arrows, and associative links with the skinny arrows. We'll see more of that later. But that is all there is in the grammar, and everything emerges from this. So I'll crack on. The neural style representation I've mentioned is essentially the spiking neural network, where events fire and they cause activation spreading in the system to trigger other nodes and neurons to fire. They spread via the network of predictive and associative links, and we'll look at how those get formed in a moment. The symbolic style representation, as I mentioned, is that perception is all represented as a symbolic style percept node. The only time percept nodes are created is when they're perceived. They're stored in the system, and they can be used as symbols and they can be used in inference, but they're never generated internally within the system. They're only ever generated as perception symbols. The behavior map. I mentioned the behavior map. This is central to the system, and it's a way that the system represents all of its interactions. So a combination of associations, temporality, behavior is what the behavior map is. And if we look at the different pieces of this, we think of a temporal map. A prediction or a temporal link given two nodes, SP, is essentially S predicts P through a form of induction. Alternatively, it can be a bind, which is an SP bind, which is also a form of induction. And they are semantically exactly the same. One is a link and one becomes a node, and that turns out to be quite useful later on. But there's no semantic difference, and the mechanism to form them is the same. And in fact, they're both formed at exactly the same time. So if S occurs and then that's followed by P, we would have a prediction with the appropriate propagation delay. We would also have a bind, which also has the appropriate propagation delay. The idea of the temporal maps is that, for example, A leads to B leads to C, which could be a form of operant conditioning, so antecedent, behavior, consequent, or simply a sequence of events. Bottom left, we see how this can be expanded as the system does inference. So given an ABC series of events, binds would be formed. For example, that A and B would be formed. And when A and B is formed, it just forms, it creates associative links to A and B from the bind of AB. And the same with like BC. So BC is formed as a bind between B and C. And again, it forms associative links between B and C. The bottom right example, a bit more complex, but essentially it's filling in recurrent connections or lateral connections as well. And the inference processors will build this temporal map, starting with the grounded temporal predictive links of ABC, and then filling in the associative links based on that temporal grounding. And we'll see why these are useful shortly. But this is kind of an incremental process that the maps get created as the system learns and adapts. Yep. Hang on, let's go back one here. Oh, there we go. There we go. Right. So, in a similar way, the associative maps are formed as well. So, everything starts from temporal grounded maps. So even associative maps begin with that. So, left-hand example, we have AC or BC with predictive links between AC and BC. It builds recurrent links between AC and BC, and from that it can then go ahead and build links between A and B, which is a form of arguably a form of similarity, but there's lots of possible interpretations here. And in the same way, you will build binds and collect binds into this map network, where there's combinations of conjunctions and associations. So these associations are associative associations, and they start to become like feature maps, or context, or depending on what it is it's experiencing, it can be a whole variety of different aspects. Ultimately, the goal here is to build what I'm calling associative temporal maps, so combinations of associative and temporal maps. This is just an example where we have nodes with propagation delays, which are the solid lines, and dotted lines are associative links. These can potentially get extremely complex, but based on the system's experience and in its implicit inference rules. So given this behavior map, which is full of relations between temporal occurrences and associations, what do we do with it? Well, it works in several ways. Bottom up, navigating this map, so from perception up through to higher level thinking, it essentially involves, it's interpreting the observed stimuli, and potentially predicting future states. So there's two aspects here. The temporal path, bottom up, is predicting what's going to happen next based on its previous history, but it's also trying to interpret what the stimuli represent, as there's many potential possibilities. So it's helping in disambiguating and supporting planning, which is a top-down process. The top-down process is priming paths based on past experience to inform the current decisions. So it's essentially trying to figure out, when I've done something in the past and I want to achieve something, what have I done? And this is the top-down intentional route. So the relation to intention aspect here is that both forward and backward movements, they align with the system's intention. And the idea is that combination of the two, where they intersect, it is what we want the system to be doing. And we'll look at more of that when we talk about the cognitive dynamics. But that's kind of the key here, is that the system's intentions are driven by a combination of top down and bottom up. I just mentioned here that negative outcomes are really important in the system. They're the key to learning and adaptation. Failed predictions modify link strengths and intentions and strategies. So the idea around this is that it's a continuously adapting model of both positive and negative feedback. And the negative feedback is, if anything, is the more important than the positive. And we'll look at how that works as we go forward. So motivation and what I'm calling affinity values. Some of you may be familiar with this theory, the valence arousal theory. It's fairly widely used in psychology to describe emotional states. Valence arousal theory essentially says that there's two dimensions to a form of classifying an experience. Valence is a scale between totally aversive to totally desirable. I will put that into a scale of 0 to 1, so 0 being completely aversive and completely desirable being 1. And arousal is, as it sounds like, it's how much effort or energy are you interested in applying here. Low arousal means it's not particularly exciting. High arousal means it's as exciting as it can get. I refer to this tuple as an affinity value. And this forms the basis for the motivation system in insight. Affinity values work at two levels. There's a system-wide affinity value that is trying to be maintained within certain levels. And it's kind of a homeostatic process whereby the system wants to maintain this affinity level at a level of arousal and valence that is kind of, it's the goal, it's the core goal of the system. And there is no other goal in the system other than it's trying to maintain this affinity value. And it does this via many other affinity values. Every node in the system has an affinity value. So essentially, each concept has its own affinity value. The system wants to represent its attitude towards every node. If you think of the attitude towards a node as being, do I like it or don't I like it? How excited am I about it when this node is valid or when this node is active? They all start out at a neutral level, and they adapt through the system's experience. Now, they don't necessarily adapt. They don't change really quickly. They change gradually. So the idea here is that the feedback the system gets, when it gets positive information that leads to effective behaviors, the affinity values improve. Let's say improve from the point of view of it becomes more desirable, and it may have a higher arousal value because it enables certain activities to occur. If it's associated with negative feedback, it may be that it turns out that we don't really want this, and it becomes more aversive. And sometimes aversive behaviours can be highly aroused because you don't want them to happen, and you definitely don't want them to happen, so you want a high arousal state. Other times it can be you don't really care, you're not interested in it, and it's a low arousal. So it doesn't have much of an impact on the system. So you have these different levels where things can be highly negative but really important, that cause inhibitory occurrences, or they can be just kind of not that interested. And eventually those things will disappear through the memory system. The main point here is that every node has an affinity value, and each of those affinity values in the nodes affect the system-wide affinity value through a cognitive behavior process. The context under which these affinity values occur is represented as a subset of the full set of neurons or nodes. Therefore, each cycle, when the system node is modified based on the current levels of the affinity nodes, the feedback also goes back to the individual nodes, and it will have a contextual component that says, the system-wide affinity value has gone up or it's gone down, and therefore, under this context, I'm also going to go up or go down. And there's this continuous feedback process around motivation about what's relevant in this context, what's not relevant in this context. So it's continuously adapting its desirabilities and aversiveness and arousal levels. Cognitive control dynamics. Again, a bit of a mouthful, but what do we mean by this? These are the key processes that control the overall system. They are what makes everything possible from an emergent perspective. We have temporal induction, we have link strength revision and merging evidence. We have the principle of assumption of failure, which deals with negative evidence or failed anticipation. And we have relative and absolute forgetting. These processes all combine and function continuously to enable the system to be self-organising, self-adapting. Just to give you a flavour of some of these, and most people are probably familiar with the ideas, but activation, spreading, and priming. When nodes fire, activation spreads throughout the network, This can be both excitatory or inhibitory, and a couple of key differences from traditional neural networks is that the activation levels can be dynamic, and the thresholds for firing can be dynamic. So there's no fixed thresholds; they're dynamic, and this enables the system to respond to resource pressures and other factors. Yeah, I won't go into too much detail. We call it connection modulation or link strengthening and weakening. The models in Insight are shown to be actually very effective. Just to give you an idea of what these graphs are, given a probability of a predictive correlation of 0.2 on this first left-hand graph, i.e., so if A follows B with a certain predictive probability, the model shows that it's very accurate. It's in this 0.20 convergence to the frequency confidence truth value of the probability distribution, and the same with this one 0.5 or 0.5 is a probability distribution, and it was 0.491, and this final one here, which was the 0.80 with a probability distribution of 0.8. So it's very accurate, converges very rapidly, and the confidence becomes high very, very quickly. So the idea of assumption of failure and the inductive prediction models was very accurate, and very pleased with that myself. Where are we? Let's go back in. Right. The idea of relative and absolute forgetting is actually, I'm short on time because I started late, so I'm going to skip some of this. Yeah, let's skip some of this as well, and we'll skip some of this. Okay, psychological processes. So the idea of emergent processes from a psychological perspective is quite key to what's going on here. There are no predetermined algorithms for any functions such as operant conditioning or relational frame theory or function transfer or substitution or any of these aspects of psychology. They're not built into the system. They emerge from the dynamics of the system. So if we look at the example of operant condition that we saw previously, that the antecedent leads to behaviour, leads to a consequence, we can see that typically in a psychology perspective, this would be represented as a stimulus with a response, with a response stimulus as a representation of how this works. We can look at this in multiple ways. We can see what we can, the predictive link representation, where we have a discriminating stimulus and a response. It's a predictive link, so SD occurs and followed by an R, the response occurs. And that is the same representation as the first part of this basic operant condition from a psychology perspective. If we move on to the next section, we can also see this as a sequential representation or a bind, where it's a pair of components. We can also look at this as a bind followed by a predictive implication to a stimulus response. And this is what I'm calling an abstract relation. This emerges in the system as an abstract relation just from the way the dynamics work. Alternatively, you can have the opposite relation. I guess it's equivalent to what we have as a intrinsic or extrinsic, accidental or intentional relation. Although that's not technically equivalent, but it's a similar idea. The representations that we have here. There's different forms that they can all be converted into. But essentially, a predictive link is a form of behavior. And everything ultimately is a behavior in this model. So whatever is linked to whatever becomes a behavior. So whilst this is expressed in terms of operant conditioning, it's essentially anything can be expressed as a form of operant conditioning in this way. And these are essentially acquired relations that the system generates automatically as a result of the way the network functions. I'm not going to go into too much of this detail. So what emerges from this model is that you can ultimately end up with classical conditioning. We've already seen you can have operant conditioning. Classical conditioning can emerge from this automatically. Function transfer, whereby different stimuli can be essentially functionally equivalent through this network. It learns this, again, automatically. It doesn't need anything other than the basic premises to learn functional equivalence. We can also learn substitution, whereby given a stimuli, we can use different responses to lead to a consequence. And again, no special mechanisms for this. This is just based on its interaction with the environment and the underlying dynamics of the system. And then the final example here is what we call a relational equivalence, whereby it's a combination of functional and substitutional equivalence. And this enables you to have higher level functions, and you can go beyond this to high levels, but they start to get very complex to draw. But the idea is that relational equivalence, so you've got equivalence between relations, which is one of the founding aspects of relational frame theory, which we also want to be able to support in the system. So briefly onto software architecture. The basis of the software architecture is something called the Cognitive Integration Module, or a CIM. They can be used in isolation if you want, or they can be used as modular building blocks to build more complex systems. And the key idea around a CIM is it's a bit like a piece of neocortex. If you think of a function area in the neocortex, it can essentially substitute for that. The idea here is that you connect different CIMs together. They all function exactly the same, but the inputs that they have determine what they become. Much like the brain's connectivity, its inputs determine how the particular area of the neocortex will function, even though the underlying substrate is all pretty much the same. So it's a similar idea here. The idea is that they can be modular, distributed, and can be interconnected on across large hardware platforms if you want to have particularly large ones. But they can work relatively effectively even on a single machine. So some examples that you can use CIMs for. I mean, you can use them as a perceptual CIM, where they can be plugged into sensor systems. You could use them as a motor CIM, where they can be plugged into motor handling. High level of integration, where you may want to have multiple CIMs connected to something. You may want to use them purely as a form of memory. But this is not exhaustive, and they can be used in flexible way depending on what it is you want to achieve. The representation is simply in and out, and that literally is all it is. It's an in and out box. The main pieces of the CIM are, there's essentially two pieces. There's the inference processor on the right-hand side, which deals with the attentional focused components and builds nodes and links focused on that particular aspect, both temporal and semantic. And then the box in the center is essentially managing the network resources and the construction of the network and belief map, and activation of the nodes. So activation spreading occurs in here. One of the things that I haven't mentioned earlier, but I mentioned at this point, is that the system is real time. So when events, when neurons spike, they arrive at the destination at the time they should arrive. There isn't any time encoding from the point of view of, they arrive early or they arrive late. They all arrive at exactly the time they're supposed to arrive. So this idea of this event delay buffer holds the list of events that are fired and sends them at the time they should be sent, so they arrive at the nodes when the nodes are due to fire. So that makes this an event-driven real-time system, which is a distinct difference to all of the other versions of NARS that we've had previously, even Alan, in fact, which was different. All right, let's have a look. So, summary: principle-driven design. All the system activity is essentially behavior. Whether or not it has a motor function, it may or may not have a motor function, but it's all behavior of some form, and it's grounded in time and correlation. There's a minimalist complexity at the functional level. So essentially all we have here is two nodes, two links, and that's it. The implicit motivation system is based on the idea of valence arousal model, system-wide at one level for the overall system motivation, and then at every node as a system's view about what that particular concept means to it. It has a neurosymbolic representation, which is both weakly connected and sparse, so it's incredibly energy efficient, but it's also powerful from the point of view of the symbolic perceptual representation enables very efficient input of high dimensional data if necessary, but it's also efficient from the point of view it's also neuro, so it works real time and in an energy efficient way. The emergence of all the key cognitive processes is a fundamental component here. It's a driver of it's driven by the underlying cognitive dynamics, but none of the actual processes related to psychology, for example, are present in the system. They are all emergent. And in a similar way, executive function, which is like the overriding control of the system, is also driven by the cognitive dynamics. There are no controls other than the system-wide cognitive dynamics. And finally, the software architecture is modular and scalable through the idea of the SIM architecture. Now, I know that has been, when I said 10,000 feet, it's probably more like 100,000 feet view of this. And if anyone's had a chance to look through the book, they may well have answered some of the questions, but I'm more than happy to take questions. And yeah, I'll pause there.
Thank you so much, Tony. So the floor is yours, or anyone who want to ask Tony questions.
We have a question from Mike.
I think Mike is applauding rather than raising his hand.
That's correct.
Everyone's shell shocked, I'm sure.
Yeah, it was a long presentation. Now, a few questions before we launch into more detailed ones. I am somewhat surprised by the spiking neural networks, and I want to understand the motivation behind bringing that into the mix to start.
Okay, so to be honest, it was already brought into the mix in the Alan implementation. I guess it depends how you look at spiking neural networks. And many of the properties of spiking neural networks are absolutely present in this system, but it's not an off-the-shelf spiking neural network. You know, it does things slightly differently to a typical spiking neural network. The key things for me were, when I looked at it, it wasn't that I meant to bring in a spiking neural network. It turned out that it just happened to become a spiking neural network as a result of what was going on. So the activation spreading was an important point. The fact that nodes had activation thresholds, that they would need the properties of neurons that would accumulate and decay action potential because of the precise timing. It turned out that when all these things of precise timing, activation spreading, activation thresholds, and a whole bunch of other stuff, it turned out that it was a spiking neural network. It wasn't that I started with a spiking neural network and said, we need to use this. It kind of came the other way around.
Okay, and the higher level motivation from that, as far as Alan was concerned, is perception deals with presents so much data, right? So it's partly an efficiency issue, right? And partly it's because of the spreading activation. It's attention control to some extent.
Or... Yes, absolutely. Yes, yeah. It definitely attention. Okay. That was the primary mechanism that was used for that.
And you couldn't see any, and essentially because you came at it through the back door, so to speak. You were essentially looking to extend NARS with, let's say, a better ability to handle large amounts of low-level data or something like that, plus attention control. Was that like a starting point?
Yeah, I mean, all of those. Yeah, I mean, it was a challenge.
Any others?
The key drivers were, as you say, it was to move NARS into the realm of what I call real perception capability, for sure. Because at the moment, it essentially handles it as more as a symbolic style, at a very high level. So it was to enable the high bandwidth perception, for true perception, as I would call it. Obviously, there's levels of that, but I wanted high bandwidth, which is what I was focusing on. The attention model, I also wanted a relatively large bandwidth on a couple of aspects. One was what to consider when forming the attentional focus. Whereas the initial NARS model was kind of an incremental, a stepwise, attentional focus. It would only select relatively few things. The idea here was that it would be able to select a lot of things, but ultimately narrow it down to a small focus. But what you had to include at the start of that process the ideal is that it would be as large as possible, given the resource constraints. These are all the things you should consider. Ultimately, though, you only want to end up with a small subset because you don't want to be multi-threading your brain at that level. You want it to be focused on a path. So that was the idea, was that you start with a broad collection of the overall set of what the related concepts are, then narrow it down to a small subset.
How far have you gotten in evaluating these ideas?
There's quite a few of the models are, in fact, all the graphs are built on mathematical models, so they all function from a mathematical perspective. I'm in the middle of a implementation at the moment, so yeah, I mean, many of the ideas are already tried and tested. So, for example, the things like assumption of failure, usefulness metrics for absolute forgetting. We've implemented these in systems already. Putting all of this together, not done yet. The one thing I have to say that is absolutely not done yet is the idea of the affinity values. It's a new idea to work with. It's different to the goal system that we've had in NAS. There aren't any goals. They don't exist as such. So it is different. And that's going to take a bit of exploring. I think ultimately the tuning of this system will be much more difficult. But I'm hoping to find ways to make that more for it to do it itself. But the fact that it requires excitatory, inhibitory, different combinations of priorities and infinity values and temporal discounting and all these kind of things, and how big the temporal focus needs to be, there will be quite a bit of experimentation. But having said that, when we worked on ONA, it was the same. It needed tuning over quite a long period of time to get really effective.
Okay, I'll stop here for to let others ask.
I have one more question. So, first of all, really nice talk. I'm really looking forward to what comes out of this. I'm just wondering, so if I got you correctly, you have percepts that take some sort of external information and that are then afterwards treated as a symbol, right? So you're losing additional information that was maybe previously within the raw data, right? By transforming it due to some rules like a YOLO that extracts some information and then transforming this into symbolic representation, right?
Right.
Okay, so if you would go into, because we are always concerned with robots and acting in the real world, if you have sensors, the noise information, for example, within sensor data, is something that carries information, right, independent of the actual measurement. Is there any sort of way where you can handle this sort of uncertainty by, keeping this information around, or is it just transformed into symbolic data and then reasoned over?
Okay, so there's a few points there. So all good observations, of course, and there are definitely things I've considered. So the first thing is that the abstraction level of the percept nodes can vary very broadly. So as I say, it can be YOLO at one end, for example, or it can be as simple as, it's a red pixel at XY. And it's not just symbolic, it's symbolic with an attached truth value. So there is a confidence factor attached to this as well. So, if there's noise and other things, I mean, you can't capture necessarily the noise. Well, I guess, you could. It would depend on the sensor system that you were using. So the idea is you would couple a specific typed percept node with the sensory system that you wanted to use with the system. So if you wanted to capture very fine grained perceptual data, including noise as a feature, you would need the sensory system to literally capture that. And then that can be input at the abstraction level that you need. So it can be a very low level abstraction, and the confidence in each of the percepts can be reflected in the incoming truth value. Much the same as, as in YOLO, it can be the confidence that, it's seen a cat. It can be like 0.85 or whatever. Whereas it can be the confidence that this pixel is red is 0.75 or whatever, or it's at this location or whatever. So it does depend on the perception system that you use, and how you encode the perceptions directly, because the type percepts are implementation specific, and they can be whatever you want them to be.
As a follow-up, how is it handling, or does it do it at all like numeric data? So really sub-symbolic data streams that are just simple, floating point values. Is this still as it was in NARS, or always was in NARS, that you kind of have to bucket it in some sort, or because it's hard to translate a numeric value into a symbolic representation, right?
Yeah, and we've thought about this over the years many times. Of course, you're right. It's been this inherent issue. One of the nice things about spiking networks is that they can represent information in different ways.
That's what I thought. Yeah.
Yeah. So the key here is that they can represent information in two ways. A spike in a typical neural network. In fact, this addresses some of Chris's questions from earlier about why a spike in neural network. A typical spike in neural network has a spike, and it's an event that occurs. In Insight, it has both priority and so kind of energy level. So in the sense that it can represent different values. So it can be a high priority spike that has a specific value, and that can represent various different things, and depending on what you want it to be. The numeric encoding can be done in a couple of ways. It can be done through timing itself. So faster timing can effectively be greater value, or it can be encoded as the value that the spike carries in terms of its intensity, or a combination of the two. So there is some flexibility there, but it's interesting because it was one of the questions I needed to address, because we've always struggled with this in terms of the numeric ones. Although as human beings, I always go back to the question, well, why do we need to do this? Because as human beings, we process numeric data, but we process it symbolically, or we either process it at a perceptual pre-processing level. So I'm not sure if it's a real problem, but it would be convenient to be able to do that for sure, because we're always trying to do it ourselves. So I agree with the spirit of the question for sure.
Thanks a lot. I mean, if no one else has questions, I'd love to discuss this a bit more, if you don't mind. I don't know, but I want to give the board to anyone else who wants to say something.
Well, no one else seems to be forthcoming at the moment, so we've still got a few minutes. So by all means, go for it.
Yeah, I mean, if you don't mind, because this is all part of my PhD, so I'm really struggling with this in some levels, because I find it interesting that you said that we as humans do stuff symbolically, because I find this fairly hard to believe. I'm more of the functionalist kind of point of view that, stuff is handled as the data that comes in and that can be transitioned into other data that will come into the future, right? And I mean, of course, our sensors that we're using are different to artificial ones. And that is something that we have to adapt to, right? If we are talking about AI systems, we need to work with artificial sensors rather than biological ones. And these data sets that come in will always be, or not always, but will probably be very subsymbolic on very level, a magnitude of levels, right? Whether it is a pixel value or a distance sensor, a laser scanner, or anything like that. And I would love to get a better insight into how your system could represent a change, for example, in a data stream of a sensor when it interacts with the world, right? So,
okay. Right.
How can this be represented that this future will be predicted, or not, or
Right. So that's a really interesting question, actually. And I guess it was slightly misleading when I said that I believe we do it symbolically. But you are, of course, right. There's a transition from the sub-symbolic at some point, which is how we perceive. We perceive sub-symbolically. And then we ultimately process at symbolic level. But there is this transition between the two. So how do you get from sub-symbolic, which is what you're actually experiencing at the raw data level, to be able to process symbolically? And the key premise of the system is, in fact, it's about behavior. So it's how we interact with our environment that enables us to form behaviors that enable us to process temporal data, which I'll call, like the sub-symbolic aspects, that allows us to transition into more symbolic forms. Now, I definitely cheat in Insight because I can. I cheat from the point of view of we can put in symbolic percepts, and if we can do that, why wouldn't we? But if you assume that there's very low-level abstractions of numeric percepts at just some signal level, it doesn't really change the model. The idea here is it's still everything's interpreted as a behavior. So the model we use here is that if everything's a behavior, it has an interaction either within the internal environment or the external environment, and at some point that ultimately enables you to ground it symbolically, but not always. I mean, from an animal perspective, you probably don't ground. An animal doesn't ground symbolically. Typically they don't learn to read. They don't do much in symbol representation. Maybe a little bit, but not much. Whereas we're much more capable. But I think ultimately it's about the symbol grounding idea of how do you ground a symbol, and it's always grounded in behavior and motivation. And there's a big chunk in the book actually about causality, where causality is relative and subjective, and that's based on motivation and behavior. Things aren't caused by stuff. You believe when you do this, based on this, that's what caused it. So it's a very different perspective. So I think ultimately there is this connection between causality, intention, behavior, and the idea of relative subjective causality that enables us to connect raw predictive correlations with something more constant, like a symbol, or at least a form of behavior. And that's a bit of a vague description. It's still kind of difficult to talk about and explain it, unfortunately. But maybe we'll be able to run some experiments around that at some point.
Yeah, I find it interesting that you bring up the symbol grounding in this. I mean, it's kind of obvious there, but that's exactly where I'm hanging with my thoughts, because I think, as you said, why wouldn't we put in symbolic data if we have the availability for it, right? We have a system that we can just put in whatever we want. But I'm wondering whether the conscious adaptation of perception based on, prediction and everything is a necessary condition for simple grounding. Because if you think about, the two parts of identification and discrimination, so first identify something in the data, and then the other thing is find something in the data, discriminate between different things. That means I must have an understanding how my percept looks like in order to get back from there to, identifying that it's actually there. So if I put a YOLO in front of it and only get the information symbolically in, I have an issue that I cannot tune my perception anymore based on my prediction, right? And assumption of insufficient knowledge and resources tells us that we don't want to compute over every single part of perception if we don't have to. So it would be really interesting if we can either disable certain percept neurons or, nodes based on what we expect the data to look like. And only if it doesn't look like it, we adjust to that, and change our behavior accordingly to the perceived information that's actually there. Because as you said, everything is what we make it to be. We think it is the cause, so we make it the cause. It's, I think, the same with perception. We think we perceive something, and therefore we perceive it, right? Because that is what we are subconsciously, consciously, however you want to call it, adjusting our perception layers for. So in my personal opinion, there must be a direction towards perception that changes according to the behavior that I want to achieve, my desired perception for this particular task or whatever we are doing right now, right?
Okay, I agree with that, and there's a section in the book under perception, which is, we call it the there is no spoon theory. So we talk about this in our talks and things. There is no spoon. The reality is we have this idea of active adaptive perception where when you perceive something, and it wouldn't be a spoon, it would be just a small piece of a spoon that like the corner of it, as an example, it's something that has a certain reflectance, and it's a thing that's there, and there's a behavior associated with this, so that the behavior would be, well, in the past when I've moved this way, I've seen this thing, and there's this consistency between the idea of an object, but there isn't really a spoon. There are just lots and lots of little behaviors that combine, that form this model, or many models of a spoon. I mean, a bit like Jeff Hawking's thousand brains theory, that the idea is that perception isn't about seeing a cat. It's about seeing many models of, when an ear does this, it might be a cat, but it might be a dog, or it might be something else. But the idea is that all these little bits of information that are behaviors all combined together, they're probably a cat, but they may not be a cat. So it is all about behavior at one level, in terms of how you're directing your perceptual senses, and how you're determining the model that's being used to, because you're never in isolation perceiving something. You're always trying to do something. There's always some intention that you're trying to fulfill as a result of this. So the intention that you're carrying out, it drives the perception as much as the perception is driving what it's perceiving. And so it's a really bottom-up, top-down thing. So, yeah, the idea of that there is no spoon for me kind of really struck a chord. I mean, I don't know, but it's from the Matrix film. Many years ago. There is no spoon, and that's what it was. It came from that. There is no spoon, and it was we had the same issue with when you're looking at stuff from a perception perspective, where does the cat come from? It's you've never seen this image of a cat before. It's different images of different bits of cat, but actually we decided in the end that there is no cat. There's just a whole bunch of behaviors that when these behaviors get combined in various ways, you more typically associate the symbol with these behavioral representations as cat, because it's linked to it's another behavior that's attached to this idea of these cat models. It's just another behavior, which is when you see these cat models, you also say cat because it's just another model of that process. It's not the symbol that represents these things. Yeah.
I love that. Yeah, a symbol is not an internal thing of this is a cat. It's more like the sum of behaviors that have been labeled with the name cat, right?
Yeah.
Love that. Thank you very much.
Okay.
Yeah, I would like to add to that. It's not just the intention. It's not just the goal that you're pursuing or set of goals, but it's also the context. And what does that really mean? Well, that really means the implications of the situation, what you can do, what you can't do. So, yes, of course, it sounds like I'm talking about affordances, but really what affordances boil down to is models of causal relations. And that actually captures the implications. And so ultimately, the meaning of any situation that an autonomous agent is in has to be based on the assumptions about what is possible and what is not possible. And so the perception derives from that. Yeah. I forgot if I had another point. I forgot it.
Okay.
Throw this out there.
No, I agree, and context is absolutely critical, of course, because the different context can mean a totally different outcome. Yeah.
And that sort of brings us full circle to the reasoning, because ultimately, you probably have all sorts of reasoning in a fully, let's say, fully equipped cognitive agent. And so I'm really curious about your ideas about these lower level, more primitive kinds of relations that somehow can be unified with higher level, but higher level, let's say, or more abstract versions of and more complete versions of reasoning. Because obviously, as you go down and you have this very small set of things and relations. There's a lot you can't do with that. So, but the interface is interesting, I think.
Yeah, and I think the reasoning works on two levels as well. There's the meta level reasoning, which is the deduction, induction, abduction, where you form new links and nodes. That's where that's the generative aspect of the model. But there's the reasoning that the cognitive dynamics allow, which is it's following the path through the activation spreading network, in the sense that it reasons based on its experience. It's a reflection of the environment, essentially. So it builds a model that makes sense on what it's experienced. So when it's navigating through the behavior map, certain things will be inhibited, certain things won't be, and therefore the path it takes through the network is a form of inference, and that is grounded in its experience with regularities, ultimately. So I think it works on these two levels of the meta level inference of the abduction, induction, deduction, and then what it's experienced is a way of reasoning. Because it doesn't make sense to do certain things because it's invalid or it's prohibited or it's whatever. So I think that does make sense. Yeah.
I'm just jumping in and saying that the meeting ends now in 30 seconds. Anyone who wants to hang out and talk with Tony, I'm sure he's available for a few more minutes.
Sure.
There are just simply too many things to be discussed, but I'll ask something relatively simple to Tony. First, congratulations for this book draft, which is much more comprehensive than your previous writing on some of the similar ideas. But I wonder, according to your own evaluation, how much do you think this current draft is done, or you think this is about the book, or is about half of the book, or what's your estimation?
Yeah, you can always do more, of course. And every time I have a discussion or work on something with somebody, I think, oh, I need to put another chapter in or change this chapter. I'm aware that it's not the best book in the world. I'm not really a writer, but I wanted to get my ideas down on paper. So from my perspective, I would say I would rather get the ideas out now and let them evolve over time if necessary, rather than just keep waiting till it's perfect. So that, I'd say, from my perspective, I'd say it was 85%.
Okay.
Yeah.
That's the number I want. For sure, there are a lot of things we agree with each other. But what I think, according to my evaluation, what is missing, at least to my interest, I think there are two key things I will expect to know. You add maybe in the last 15% or how much. One is abstraction. That's actually, to me, what the previous question and is mostly about. And we all agree that perception and cognition should be unified. And I fully understand your stress on sensory motor. You want to start from the front end. That's understandable. And I also agree that in a sense you can say that all the relations, conceptual relations, start from a temporal and a spatial relationship. So you focus on, for now at least, on temporal and use a spatial neural network, a version of to do that, which is understandable. But on the other hand, when you move up in this level of abstractions, you are going to need to, you can call it comprise or summarize or whatever, which means you are going to drop some of the information, for example, temporal information. So I don't feel very comfortable with the stress on temporal information to the degree it seems like everything, all the knowledge need to have the temporal aspect in that. Which I understand where it comes from. I understand the crucial importance for sensory motor. But when you're moving up, the problem is a lot of different temporal pattern will actually be treated as the same. We are going to drop the detail because it's not really relevant whether there's two things, 2 seconds apart or 3 seconds apart. To us, that's to some of the operations not relevant. For example, you have this parameter, this delta t in your writing about the temporal distance. You didn't mention whether that's a default or whether that's a parameter that changes from time to time. And when you're doing revision, whether you can treat different delta t to be the same or more or less the same. Or you do some kind of like what we did, some kind of projection. And that's, for example, that's one example.
Yeah.
Another example is I don't see whether you have any long-term task in the model. Instead, to me, is more like event-driven. You have current input, and you process that, you go through this neural network. But whether at the high-level cognition, you clearly will need to have long-term tasks. And you said you don't have goals, which I can understand. You have something else which kind of like built into the system as a parameter, and you judge your behavior according to that. That's also, of course, possible. But on one hand, whether that's really you want the system to have a fixed top level, you can call it motivation or drive or goal or not. That's one. It's part of kind of like a philosophical. Another part is whether you have that. Then another thing I don't see much discussion is the control part. That's kind of like the current big issue in NARS, but I don't see. I kind of like know your idea, but I still want to see, for example, for something you have several possibilities. And are you going to try one after another, or are you going to make a commitment, always try the most likely and you ignore the other, or you do time sharing, or you do dynamic resource allocation, and so on. I don't think we have the time to discuss all those things in this meeting, but I just want you to know that which part I'm looking forward in your architecture. That's it.
Okay, very quickly on the last bit about the control. It's interesting because I would consider the control, well, the cognitive dynamics, as I call them, to be the most mature and complete aspect of the system. From my perspective, that's pretty solid. But I agree with many of your other points. For example, I would say the weakest part of the system is the motor aspect, so how sensory motor integrates. I've never liked the approach that we had with ONA, for example, where we use this idea of motor babbling. It works for a very limited subset of motor functions, but it can't work if you have a more complex physical system. So I needed something else. So I went with the idea of humans, in the sense that reflex behaviours. It learns from reflexes and then learns to inhibit them over time. But it's not perfect, and I definitely think there could be a better approach to that. The questions around your first points. I guess it does depend on your perspective on this. The ideas around abstraction, essentially, that I think the system has to learn a lot more information than a typical NARS system would have to have done in the past. I think it really needs to learn to behave and to think and how to function mentally. Whereas a lot of the processes in NARS, because of the semantics of the grammar and other things, it kind of has those built in at the meta level. Clearly, that isn't the case with Insight. And I'm aware that the system needs more experience, more time, and it has to learn its own internal processes as behaviors in a more complex way, well, in a more thorough way, should we say, than the NARS has to do, because it's not there, it's not built in. Now, at this stage, I can't say whether that will work or not, for sure. The idea of the emergent processes, it's modelled, this modelled from the point of view of psychological processes, and ultimately, I think it will work, but I can't give you any empirical evidence at this stage. Some examples like, there aren't variables. So generalization is a very different process. So in fact, it's a leaf out of your book, which is, we just use substitution at ever more complex levels as a way of removing the need for variables, and use substitution as an alternative mechanism. Although, having said that, there are some anonymous variables that enable perception to work a bit more effectively, but no generalized variables. And I think, as you said, this is a really long discussion, and we could be speaking for hours, really. I guess the key thing is, until it's fully fleshed out and built, it's a theory, and until there's any empirical evidence, I can't support it with anything other than my own thought process around this at this stage.
What's your timeline for that?
That's a good question. I mean, to be honest, it's not a particularly complex system. So, I mean, you know, I'd say half done. So maybe a month or two to have something functional. But then, of course, you know, it's always, as with these things, they're always refine and increment. So it won't be done in 2 months, but there'll be something that functions in 2 months.
Great. Thank you so much, Tony. So in 4 weeks, we have, is it you, Pei, that will present or someone else?
Probably it will be me. Yeah.
Okay, great. Will you send out some title and abstract and things like that?
Yeah, I will send out an abstract. For now, I'm thinking about to talk about the reasoning in large language model.
Great.
Sounds good.
Yeah. If you send the abstract to me and title, I can use the same email list we used this time if you want. Great. Thanks everyone for today.
Okay.
See you. Thank you, Tony.
Thanks, everybody.
Bye-bye.
Bye.
Thank you, everybody. Bye-bye.
Thanks so much.
Thank you.